Everybody, so today we're going to talk about electric dipoles, and we're specifically going to be looking at example 21.13 from page 709 of your textbook. So we've gone ahead and drawn the example here on the page already. But what is an electric dipole? An electric dipole, as you can see on the page, is two opposite but equal charges separated by a set distance. So we're going to go ahead and label our positive and negative charges Q and negative q respectively, since they're opposite but equal. And we're going to label the distance between them as d. But what we're really going to be looking at in this specific example is this dipole's interaction with a uniform electric field, which we're going to label E, with a little vector with an arrow over it. So now for some numbers. In this specific problem, our charge is 1.6 times 10 to the negative 19 coulombs. And the negative charge is going to be the same, but negative. Our distance is 0.125 times 10 to the negative 9 meters. And our electric field is going to equal to 5 times 10 to the 5 newtons per coulomb. So, in part A of our example, we're going to be looking at the net force exerted on the dipole. So, if we are looking at our force, we're going to calculate it by using the magnitude of the field times the magnitude of our charges. So, because the field is uniform in every single area, and our charges are both equal but opposite, we are going to get two forces on the dipole that are equal but opposite. When we add them together, we're going to find that these forces are equal to 0. Okay, so in part B of our example, we're going to be looking at the electric dipole moment. Now, the electric dipole moment is kind of your electricity and magnetism equivalent of moment of inertia, and later on it's going to help us calculate the torque done on the electric dipole by the electric field. But for now, we just want to find the measurements of it. So there are two components to your electric dipole moment. There's a magnitude and a direction. Now, when we're looking at the magnitude, we are going to take one of the charges, and we are going to multiply it by the distance between the two charges. So P is equal to Q times D, which in this case is equal to 1.6 times 10 to the negative 19 coulombs times 0.125 times 10 to the negative 9 meters. And we're going to end up with 2 times 10 to the negative 29 coulomb meters. So after we do that, we have to find the direction of the electric dipole moment. So the electric dipole moment is measured in reference to both the direction of the electric field and the orientation of the dipole. A dipole, as a general standard, is always measured from the negative charge to the positive charge. So our dipole moment, let's set up this thing over here, will go in this direction. Awesome. And we're going to measure it in relation to the electric field. So you're going to take this angle between these two vectors. Awesome. So in this specific example, this angle is 145 degrees. So in part C of the example, we're going to be looking for the magnitude of torque on the electric dipole. Now, this is calculated using the electric dipole moment, as we mentioned earlier, and the magnitude of the electric field. The exact formula that we're going to be using is that the torque is equal to the electric dipole moment's magnitude times the electric field's magnitude times sine of theta, when theta is, like I mentioned earlier, that direction or orientation of the dipole in relation to the electric field. So in this specific equation, this is equal to 2 times 10 to the negative 29 coulomb meters times 5 times 10 to the power 5 newtons per coulomb times sine of 145 degrees. Which is equal to 5.7 times 10 to the negative 24 newtons times meters. In part D, we're going to be looking at the total potential energy that the electric dipole has at this moment. Now, we're going to call this U, and U is equal to negative P, that's the magnitude of the electric dipole moment's arm, times electric field, E, times cosine of theta, which in this case is equal to 2 times 10 to the negative 29 coulomb meters times 5 times 10 to the power 5 newtons per coulomb times cosine of 145 degrees, which is equal to 8.2 times 10 to the power of negative 24 joules. Keep in mind that this is in reference to 0 joules, being when the dipole is at 90 degrees in relation to the electric field.